Okay, I think we're going to go ahead and get started. Welcome to the first Nano at Tech seminar for the fall 2022 semester. Before I welcome today's speaker, just a word about our next seminar, which will be 2 weeks from today on September 27th. And the speaker will be Yunan Shah from the Department of Biomedical Engineering and School of Chemistry and Biochemistry. So it's a real pleasure to welcome back prodigal son, I guess, of Georgia Tech, Spyros Pavlidis. Spyros, and actually, I forgot to ask you, where did you get your bachelor's degree?
I was in England at Imperial College.
Imperial College, and then got his master's degree also at Imperial College London before coming to Georgia Tech, where he got his Ph.D. in electrical and computer engineering, and then stayed on for a postdoc in material science and engineering before starting at NC State, where he's currently an assistant professor in the Department of Electrical and Computer Engineering. He's also associated with a couple of big centers, namely the Power America, which is part of the Manufacturing USA network, as well as the Assist Center, which is an NSF ERC. 2022 has been a good year so far. He had a number of awards, including Bennett Faculty Fellow, as well as an NSF Career Award. So I think can only get better from here. So and with that, I'll turn it over to Spyro.
Wonderful. Thank you very much for the intro. Yeah, so I'm very excited to be here. A lot of familiar faces, and feels sort of strange for me to be on this side of the podium. I was used for a long time to be sitting in the audience there, eating a slice of pizza or something while watching these talks. So it's nice to be on this side of the podium as well. So yeah, I'm going to be talking today about the work that I've been doing at NC State for the last few years. One of the main thrusts of my group has been to focus on the development of gallium nitride devices, and a big part of this has been enabling next generation vertical GaN power devices using selective-area doping techniques. So a couple words, I guess, about my group before I jump into the technical detail. When I moved to NC State, I started a group or a lab, and we call ourselves NCSU LEADS, which stands for Laboratory for Electronics and Advanced Devices and Systems. So there's a lot of words in there, a lot of things that you could, I guess, interpret from that. But this diagram aims to kind of give you a sense of what we're doing. At the core of it is development of devices, electronic devices, high-performance devices. And you can see that that really intersects with a lot of other areas as well. So as was mentioned, I got my degree in ECE, but I also spent some time working with Eric's group as well in material science. And I think one thing I've come to appreciate very, very much is the importance of good material to enable a very good device. And so we work closely with material scientists to understand how their synthesis approaches or their new technologies can enable new devices and better performance in these devices. And of course, all these devices ultimately have to trickle their way up into circuits and systems, and so we look to collaborate with other folks on that and also do some basic demonstrators sometimes with circuits as well. And big picture, all of this has to lead to some sort of progress, some sort of societal change or improvement. And in the context of what I'll be talking about today, it'll be for power devices. And I'm sure many of you are well aware of the importance of power devices and power systems. They really form the backbone of our modern society, right? Ranging from the integration of renewable energy sources to novel transport, to resiliency, and you name it, it really touches all the different areas of our lives. So what we're really thinking about here is opportunities to improve efficiency, to improve performance, and reliability as well, and unlock even new applications for solid-state devices to find their way into. So this is an outline of what I'll be talking about today. It's sort of a high-level outline. I'll start off by giving a brief introduction to power devices. I understand that there's a broad community here in the audience, so I want to make sure that we're all on the same page about what I'm thinking about when I talk about power devices. And as the title already hinted at, there's a really strong need for selective-area doping. And for GaN has a lot of attractive properties that make it a great fit for power devices, but a big technological challenge for a long time has been the ability to dope areas of the device laterally with different selective-area doping techniques. And so that's one of the things that I'll be touching on today. And the two devices that I'll focus on to demonstrate that are a gallium nitride superjunction device using a structure known as a lateral polar junction. I'll give a bit more information about that later. And then a JBS diode with implantation and ultra-high pressure annealing. And so these are different doping techniques, different ways of doping GaN devices in different regions and different devices that go along with that. And I also want to highlight some very, very important people that have been involved in this work. Dollar and Shane are two of my first students. Dollar actually graduated recently, and so a lot of the work that you'll see is his work that he was driving, spending a lot of time in the clean room, testing devices as well, and Shane has been following up a lot of that work as well. And then I mentioned earlier the importance of good material and collaborations with material scientists. Slatko Sitar and Ramon Collazo in the material science department at NC State have been really key collaborators in the work that you'll see here. And our groups really overlap quite a bit and work closely together, so I want to make sure that they're acknowledged. So GaN, if you're in the world of wide bandgap semiconductors and power devices, you've probably seen a chart or a table like this before. But again, if you're not, I want to make sure that you're aware of why we're talking about GaN in this context. So there is a few different properties that we can kind of stack side by side when we compare gallium nitride with silicon, conventional silicon devices. The first is looking at the bandgap. Clearly, gallium nitride has a larger bandgap. That makes it why we call it a wide bandgap semiconductor effectively. And if you skip to the bottom of this table here, the second to last row, you can see a clear relationship between the bandgap and the critical electric field. And that is the main property that we are really trying to leverage here as we scale these devices and try to make them more efficient. Now, one of the figures of merit, this is the Baliga figure of merit that a lot of people cite when discussing wide bandgap semiconductors. You can see here as a very important and cubic dependence on critical electric field. And so clearly, once you have a couple factors of improvement there in critical electric field, that very quickly translates to a blown up reason to go after gallium nitride. Now, I would never make the argument that you'll get a 4,000x improvement in a gallium nitride device versus silicon, but I think the leap here is large enough that you can motivate the idea of going after this and see something like a 10x improvement, for example, in performance. More qualitatively, what are we looking for, or what do we gain? Well, if you look at a unipolar device or a Schottky diode as an example, what you're doing is you go from a conventional silicon device where this drift region here, this is a low dope and thick region in the device that has to sustain the electric field. That region can be redesigned in gallium nitride or wide bandgap semiconductors more generally to be thinner and higher doped. And so that ultimately reduces your drift region resistance, and if that plays a key part in your device's overall loss, and will really reduce the losses in your device as well. And so this has an important outcome. Not only are we improving conduction losses and lowering RON, but it now means that we can think about using unipolar devices like a Schottky diode or a MOSFET in place of other bipolar devices. So IGBTs, for example, are devices that are typically use silicon IGBTs, and now we can think about replacing IGBTs with MOSFETs or other unipolar devices. And that has system-level outcomes as well. So unipolar devices can switch faster, and by switching faster, we can miniaturize the size of the system. And so that then unlocks the opportunity to go after very mobile applications or applications where size and weight are big constraints. So this is another way that we sort of visualize this, and you'll see curves like this show up in my presentation and a lot of other presentations as well. Basically, we're able to draw a relationship between RON and breakdown voltage for different technologies. When you go through and work through different materials, you'll find different coefficients here, and then this breakdown voltage relationship with RON with a power of 5/2, and that kind of gives you this slope that you see constant. But overall, what you're seeing is that you are shifting down to the bottom right-hand corner of this curve, and clearly for a same constant breakdown voltage for a wider bandgap device, you're able to reduce your conduction losses. So this is really why GaN is exciting. But one of the things that I want to highlight here, and this will be especially important when I start talking about the superjunction devices, is that, as it is noted here, the relationship between breakdown voltage and R-on is pretty fundamental. You scale it by material parameters like the critical electric field, but this slope is basically the same. And so the superjunction device that I'll talk about later, one of the things that we are looking to do there is actually bend this curve downwards and get even more efficiency, even lower loss for the same breakdown voltage. So we're trying to go beyond those conventional relationships and rules. So I promised you that I would talk a little bit about the need for selective area doping. And so these are some devices that are very relevant to power. What you have is the JBS diode, or the junction barrier Schottky diode, that I already sort of talked a little bit about in my outline. You can see here that this is basically a Schottky diode. There's a Schottky contactor here at the top, but underneath that there's a grid of a P-type doped regions, as well as these regions off this side. These are floating field rings that are often used as well to improve the edge termination efficiency, or basic electric field distribution of the device. And so you can see here that, yes, we have N-type doping, and that needs to be very well controlled, but we also have a need to make lateral p-in junctions for these devices to work. And so there's an important question about how we do this. JFET, same kind of thing here. You need junction terminations, you need P-gate as well. And then another one over here, which is one of the another device that I'll focus on today, is a superjunction diode, where you have these lateral p-in junction regions to alter the distribution of electric field and improve the performance of the device. So clearly, throughout all of these, and even other devices as well, you need to be able to introduce regions of p-type doping laterally within the device structure. And this has been traditionally a very big challenge for gallium nitride. So one of the reasons is that, with silicon, one of the things we typically learn when we learn about semiconductor fabrication is we can leverage something like diffusion doping, right? And so that's a very convenient way to get started. But with gallium nitride, that's not an option. These diffusion processes are very, very slow, so it's not practical to use them. You can also deteriorate the surface with those high temperatures that are needed. And then another very common practice that's used, especially in cases like this, is etch and regrowth, and that etch and regrowth process can lead to damaged interfaces, and then that can also reduce the performance of your device. So we want to think about other ways of doing that, and I'm going to talk about two of those ways today. So let's start off with the gallium nitride superjunction device, and the structure that we're going to use there is the lateral polar junction. So I already showed you this chart, and I just want to remind you one of the main outcomes here is that there's this fixed trade-off or relationship between R-on and breakdown voltage for unipolar devices. And what I want to do now is think about how we can break that rule. And let's build up to that by looking at where this comes from. So in a conventional unipolar device, like a Schottky diode here, you have this low-doped region underneath your Schottky contact, underneath your anode, and you are distributing the electric field across that. And so what you're trying to do is basically make sure that you do not hit your critical electric field of your material too early, otherwise you'd have premature breakdown of your device. And the slope of this triangular distribution of, or linear distribution of electric field is proportional to your doping. So generally speaking, you lower the doping and then lower that slope as well. And the design rules that you'll see, and this is pretty generic, the numbers are tuned to GaN here, but the relationships are fundamentally the same and across all semiconductors, is that as you go to a larger breakdown voltage, you've got to do a couple things. The first is that you've got to reduce your doping concentration. I already sort of alluded to that over here. And the other is that you also have to scale up your drift region thickness. So you can see as an example that if you want to make a device that is 5 kV, for example, you have to be into the 10 to the 15 range, which is very, very difficult. You have to have very well-controlled growth processes, control over impurity incorporation. And if you're going to do this for high voltages, you need to be able to grow layers that are tens of microns thick. And so ideally, you don't want to do that with a very, very slow deposition process either. That'll take forever. So we want to be able to achieve low doping. We want to also have low doping in combination with high mobility. If you have a lot of impurities that you're either purposely or unintentionally using as compensators, those will ultimately also lead to a hit in your mobility and therefore your losses. And if you can, you need to think about ways to do this with high growth rates. But this is sort of the challenge that everyone is dealing with when you try to make a unipolar device. So is there another way forward that alters your design rules, that gives you another way to scale up and make high voltage devices? And that's where this superjunction structure comes from. And this is a little bit of discussion about reverse bias design and behavior. So the superjunction, unlike the Schottky diode that I showed you earlier, now has these lateral pillars or stripes of P and N regions side by side. And so when you look at the electric field distribution, it goes from being this linear or triangular shape that you had before to now having this rectangular shape. So vertically, there's basically a doping independence, and it's laterally now that you start to see that triangular shape come out, where now doping and width of those stripes, these WP and WN layer parameters, become very, very important. So we're kind of flipping this structure over a little bit in terms of what we have to think about with doping requirements. And we did a lot of analysis, and others have done this as well, to understand how these relationships work for gallium nitride. And these are some examples to kind of give you a very direct feeling of what the benefits are. So let's take the 5 kV case. If you're doing this with a unipolar device, again, you'd have to be in the mid 10 to the 15 doping range, so very low doping with thick 35 micrometer thick drift regions. Now, if you're you've got a superjunction device, and you can scale this to have very small pillar widths, now your doping relaxes, and you can do this at 317, and a slight improvement or relaxation of your thickness requirements as well. But really the main benefit, as you can see here, is almost a 2 orders of magnitude increase in the doping that you need. So that relaxation in doping requirements means that we can do this with technologies that are available today, and devices can be made from a doping perspective alone. But the big problem that you'll see here is, again, how do I do that with selective area doping, right? So I can make an N-type region that has 10 to the 17 doping, yes, but how do I make these stripes side by side so I can make the superjunction work? So overall, those larger doping levels lead to smaller R-on and better efficiency. And then the other really critical thing that you have to think about when you're designing and making a superjunction is charge balance, or the other way around, be worried about not having charge imbalance. Because the math on how these devices work assumes that your charge is balanced between your lateral p and junction regions. And you can see the consequence of not having that in this chart here. If you start to deviate from a charged balance scenario, you see a roll-off in your breakdown voltage. And the other really important thing to keep in mind here is that that slope, or that roll-off, is very dependent on the doping level that you're using. I mentioned earlier I want to have a high doping level to reduce my losses, but you can see here that now puts me in a very risky position. The higher doping I'm using, the more aggressive that roll-off becomes as well. So the need for charge balance becomes even more important. So this really places a critical need on doping, and then being able to control doping in both of those P and N regions side by side. And you can see another consequence of that happening here. If I start to see charge imbalance happen, I start to move more to a 1D case, and I can see, a very significant reduction in my breakdown voltage, and basically a complete collapse of the superjunction feature that you get with these devices. Now, the other side of the coin is also thinking about how these devices behave in forward bias. So, with the Schottky diode, one of the great things about it is that your turn-on voltage will generally be low. It'll be dependent on the properties of this metal semiconductor contact, and current will flow through that drift region if you apply a large enough bias, and you'll be majority carrier flow or unipolar current through there. In the superjunction case, you now have 2 regions, and basically 2 important barriers to think about. One is going to be that top metal semiconductor barrier, which is that same Schottky barrier over here. And then you have another p-n junction down here. So the idea is to be biasing, able to turn on your device or engineer that Schottky barrier to be somewhere between that p-n junction, below that p-n junction, and then still get high current flow with low turn-on voltage or low forward voltage drop to keep your efficiencies low as well. And we want to avoid getting into the p-n junction regime where we have bipolar action happening. The challenge as well, though, is thinking about how to engineer this so that your turn-on voltage is not too low, because if that barrier becomes too low, then your reverse leakage currents also become significant, and you have issues with the efficiency of your device and blocking. So also thinking about Schottky barrier height engineering is important here, and I'll address that later too. So, I'll show a couple of these charts here just to kind of drive this message home. When we went through and analyzed these devices for different geometries and so on, we can come up with these analytical equations to very quickly understand what the benefits of the superjunction device are. And you can now see what I was talking about earlier in terms of breaking that slope. That conventional 1D limit is here with that conventional relationship between breakdown voltage and Ron. And when we get to the superjunction, we see a new relationship, and that relationship has an extra tuning parameter, which is the pillar width. Clearly, if I can scale these devices down to smaller pillar widths, I can see even more benefits in my performance. So we have to think about ways that we can control doping, control the incorporation of doping in different regions, but also, can we do this in a way that can be scaled down to very small pillar widths? If we do that, then we can improve the performance of our devices. And so we're looking at trying to make these 1 micron pillar widths, or potentially even smaller in the future. And like I mentioned earlier, engineering the various parts of the device here. So to put this into context, why I'm going to talk about the lateral polar junction approach, but to understand why this is so different, you have to understand how people make these things, right, today and with conventional technologies. Namely in silicon, but also some of these things are being translated over to silicon carbide, which is probably GaN's biggest competitor at the moment in the wide bandgap market. So one of the approaches that is used is to do something like a multiple epitaxy approach, where you sequentially grow a film, implant into it, grow another film, implant into it. And if you're in silicon, you can also leverage diffusion of the species to merge all these things and create a continuous p-n junction as well. Silicon carbide and GaN don't really have that. You basically don't have significant diffusion there. Well, silicon carbide, actually, I'll show why GaN may actually have a pathway for that later. But all of this requires very well-controlled litho, because you have to do this multiple times, efficient activation of implanted species, and in order not to do this too many times, hopefully the ability to implant in a very deep level as well. You can also do trench etching and regrowth. So you etch out a region and put in a layer within that. That not only requires good litho, but also requires high-quality interfaces. And we can't do wet etching in GaN, and we have to use dry etching. Those dry etching processes usually leave behind some type of damage. Those interfaces are going to have defects, and then those can be leaky interfaces, and then also lead to problems with the device performance. So with GaN, it's really hard to look at what people have conventionally done and just do a one-for-one swap for processes. We have to think about a new way to handle this. So when we were all talking, and Zlatko and Ramon have been thinking about this for a long time as well, there was this idea of leveraging a unique property of gallium nitride, which is the fact that GaN is a polar material, and you can basically grow it, either gallium polar or nitrogen polar, which basically is, you can see, comes about as a result of the differences in the direction of the polarization fields there. And there's a few important consequences of thinking about gallium polar and nitrogen polar. They're essentially the same material, but they actually have some different properties, which almost you can treat them as different materials in a way. I mean, from an electrical engineering perspective, in some ways they almost behave like very different materials. Because of the difference in the direction of the polarization fields, actually when you make a contact in nitrogen polar GaN, you have a different barrier height, so different Schottky barrier height and different turn-on voltage for your diode. And so that brings in already hints that we have to think about how to engineer that interface. Chemical sensitivity is very, very different for nitrogen polar GaN. So conventionally for GaN, you have to dry etch it, and you can expose it to a lot of different acids, and it'll survive quite nicely. Nitrogen polar GaN is very, very sensitive to acids and bases. I'll show a little bit of that later as well, but to kind of make this clear is that early way of understanding whether you grew nitrogen polar or gallium polar GaN was just to dip it in KOH, and if you started seeing etching, it was nitrogen polar GaN. So it's that easy to see it. Another very important feature is asymmetric defect incorporation. Gallium polar GaN, when you're doing growth, like MOCVD for example, if you can tune it so that the growth conditions incorporate a low amount of oxygen, a low amount of background oxygen. With nitrogen polar GaN, you'll generally see more oxygen being incorporated. So now you can think a little bit about how doping might be different in these two types of orientations. And so that's where the lateral polar junction comes in. we can take a template, a nitride template, pattern it, and then now go directly to a growth step where we can grow gallium polar and nitrogen polar layers or regions side by side in a single growth step. And in doing that, while doing that, I can, for example, introduce magnesium as a acceptor impurity. And for the gallium polar regions, there will be low background oxygen. Magnesium will be incorporated. That material or region will become p-type. Whereas for the nitrogen polar regions, I'll still have oxygen incorporated in there, which will be net n-type. And so I can basically create N and P regions side by side with each other. And this is really a very different approach compared to what you see in conventional fabrication techniques with implantation and so on. We can do this in a single growth step. And as a result, that also leads to the ability to scale this down even further. We can do a single litho. You can use something like EBL, for example, in the future and get submicron features and not have to worry about layer-to-layer alignment and multiple lithography steps along the way. So, okay, we have the structure. We can grow this to some degree. But what is kind of missing here? So we need to be able to demonstrate sort of 317 doping. I mentioned that number earlier to be able to be relevant for kilovolt range types of devices. We need to be able to do that for 1 micron features or smaller. We need charge balance, which is really important. And we want to think about Schottky contact engineering so we have low reverse leakage currents as well. So for nitrogen polar Schottky diodes, this is one of the first papers that we published in my group. We went through and made these N-polar, we worked with Ramon and Zlatko who grew these N-polar regions, and then we went ahead and made Schottky diodes on these devices. And the goal was to demonstrate mid 10 to the 17 doping. So we went through when we made these devices, we characterized these as a control on sort of unprocessed, pristine surfaces, if you will. And we set a baseline for very high quality Schottky diodes with low ideality factors. And now you can see turn on or threshold voltage of 0.4 volts. Gallium polar GaN typically has a larger turn on voltage when you make Schottky diodes on in the range of 0.6 to 0.7 volts or so. So this is already a little lower, and you can see that that will trickle down later when we make these devices for high voltage applications. We also, in this same paper, did CV, and from the CV we could confirm that with the growth conditions that were used, we now had N-type doping effectively a 317 range. So this was in that range that we needed to be able to make these superjunction devices down the line with high voltage behavior. Another important study that we did as part of this paper was looking at the impact of our processing. So conventionally, when you make a high-quality Schottky contact, you want to prepare the surface before metal deposition, and that often involves treating the surface with some sort of acid to clean up oxides or residual carbon, for example. And a very common way of doing that is a hot HCl bath. And you can see here, these are SEMs side by side of different surfaces after different chemical treatments. That will immediately lead to very rough surfaces, damaging that interface before you put the metal down. What that does is increase your barrier height. And you can even see this coming about if you use something like TMAH, which of course is a common base in developers for litho, right? So we even have to think about how we do our lithography in these kinds of processes. So this is very, very sensitive, right, as far as the material is concerned and the way that the processing is done. So that has impacted a lot of the ways that we've done our processing down the line as well. So we've shown now that you can make a high-quality Schottky contact if you control the surface and keep it clean. Demonstrated relevant doping levels, but also showed that there's sort of a low barrier there that could lead to leaky currents. And so we want to increase that barrier height and think about ways to improve chemical and thermal stability. So one of the things that we leverage for this is making a thin silicon nitride inner layer, and we specifically have been doing this with low pressure chemical vapor deposition. And so this was another study that we published where we deposited these LPCVD layers relatively thin at 7 nanometers and then put down our Schottky contacts on top. And in this case, we also looked at different surface treatments to that silicon nitride prior to Schottky metal deposition. One case where we dipped the samples in HF to remove oxides that were forming there at the surface, and another one where we let the oxide grow after letting it the sample sit out for a few days, and then put the Schottky contact down. And you can see that this has a very important implication on the device's performance. This curve here, the red one, is this sample with the oxygen-terminated surface with a large turn-on voltage. But if you use HF to treat the silicon nitride before putting down your Schottky contact, your turn-on of that HF clean surface is slightly higher than your bare or control device, but you still get high ideality factors, and the silicon nitride is just a thin inner layer there as well. So what did we conclude from this? I'll just briefly mention this. This was an interesting sort of interpretation where we sat down, and there's other results in this paper here as well where we did XPS and other techniques. But basically, we were able to understand that depending on what the surface termination is and how you treat that surface, the dominant barrier will either be at the surface, which is this oxygen-terminated case where you have a large barrier here at the surface, or that surface barrier will be quite small and the dominant barrier will be at that interface below there where the silicon nitride and GaN is. And so you have to be very careful about how you treat these samples and how you fabricate them, and then ultimately that will have an impact on their performance as well. Now, not only did we tune the barrier to be larger through the inclusion of that inner layer, but we also demonstrate that we can now go to higher temperatures. And so I'll just briefly show this here. This was a control device that already at 250 degrees was basically resistive. I mean, there's no rectification effectively in this device. But with a 5 nanometer silicon nitride layer, we can still see a rectifying diode at 400 degrees Celsius. And so that takes advantage of the larger barrier height that we're engineering through the inclusion of the silicon nitride layer. And we even showed that if you go to 500 degrees Celsius, your device still survives. It does change a little bit in its behavior, so you probably wouldn't want to do this on an everyday basis, but you can deploy these devices at hundreds of degrees and still see diode-like behavior. And when we looked at trying to understand what was going on here, we can see that there's a little bit of a change in surface morphology there. And at the temperatures that we're working with here, there is well-documented alloying between nickel and silicon. So we think that we've created some sort of silicide at the interface there. So the reaction is probably more to do with the metal to silicon nitride interface changing rather than the underlying silicon nitride to GaN interface. So that is all well and good because we can show low ideality factors and engineered interfaces and so on. Because the inner layer is so thin, we have negligible change in the on resistance as well. But the biggest problem in terms of high voltage is that if you use the silicon nitride layer, ultimately you might see breakdown happening or bottlenecked by your dielectric. So we were thinking about a different way that we can do this that would really leverage the wide bandgap properties of gallium nitride, but still allow us to tune that barrier height and get better performance. So the idea here is to use what's known as a camel diode, and that's what I'll talk about here. So this is, again, your conventional Schottky contact or Schottky diode. And the camel diode is sort of a hybrid or in-between state almost of a Schottky and PN diode. Effectively what you're doing is you're introducing a highly doped P-GaN layer beneath your N layer and your Schottky contact. But you control the thickness of that so that you are able to introduce this hump in the conduction band and therefore a larger barrier compared to your conventional or reference Schottky diode, but you don't go all the way to the point of turning this into a PN diode. So this becomes a depleted layer effectively. And we did various TCAD simulations to look at how this relationship exists between thickness and as well as we go to this chart between thickness and doping. So there's two sort of design knobs there that you can use. But effectively, this gives you a way to kind of add to your reference Schottky barrier diode, your Schottky barrier for your barrier height for your Schottky diode, and kind of add to it via engineering this P layer. So that's what we aim to do here, and we kind of design this structure where we introduce this thin P-GaN layer with very high doping on top of now the lateral polar junction with the gallium polar and the nitrogen polar regions side by side. And this was meant now to start to prove out the different concepts that we have here in terms of making our way towards the superjunction structure. So you can see here a cross-sectional SEM, and you can actually make out the various regions of the device. The gallium polar region is here, and the nitrogen polar region is here. So We then went ahead and analyzed this in a few different ways. The first is we did what people normally do when they want to make sure they have nitrogen polar GaN, which is we dip this in hot KOH, and indeed we can see selective etching. So we can see that we are removing these pillars where the nitrogen polar GaN was grown. So you can see a periodic arrangement of these nitrogen polar and gallium polar domains side by side. And if you zoom in and do a TM on this cross-section, at this scale, you can see that there's a very abrupt interface between nitrogen polar and gallium polar as well. So these are atomically abrupt inversion domain boundaries as well. I mean, full disclosure, I would say we still have some work to do at a macro scale, right? You can see there's a bit of a roughness there along that edge, but at this scale here, there's good control of these inversion domain boundaries. And then we wanted to think about charge balance or impurity incorporation. And so we did a SIMS scan here to look at depth analysis. And we tracked magnesium through this structure here. And you can see that there's a 1E18 level. And keep in mind that when we're sampling the SIMS here, we're doing it across a large area. So it's capturing impurities that would be both in the nitrogen polar GaN regions and the gallium polar GaN regions. So we're calculating or seeing about 1E18 in these regions. And then we're also seeing about 2E18 from in oxygen. But we know that there is very low oxygen coming from the gallium polar region. So we can attribute the magnesium from both regions and the oxygen from only the nitrogen polar region where it is predominantly being incorporated. When you go through and do the math on that, you basically now see that you have this charge or impurity balance of 1E18, N-type, and P-type between the two regions here. So this was, very happy result for us to see that the doping is being controlled well at these dimensions, and then we're able to kind of move forward here with characterizing this device. Now you can also see that for this structure, we did not hit sort of the low 1E17 range that we wanted. So there's clearly work to do to not just control the charge or the impurity incorporation in both regions, which is what we're achieving here, but to do that while also reducing the doping. So we can hit low doping when we're only growing nitrogen polar GaN, but the moment that we try to put these two together now, it becomes a more challenging proposition. So that's one of the big areas that we're all working on right now as we work with the material science team. Of course, I'm an electrical engineer, so I wanted to take this device and make something with it, or these layers, and make a device on it. So we made Schottky diodes on these. These are the IV curves that you see here. You can see that we have a larger turn-on voltage, greater than a volt, which we attribute to this camel diode structure that we have here. We also did some simulations to try to understand what combination of thickness and doping best matches that. And you can see here that it's not what we found as the best fit. It's MIDI 518 Na and 15 nanometers thickness, which is different than what we intended up here. So that also leads us to now think a little bit more carefully about how we control the growth to get abrupt interfaces. For those of you that are familiar with gallium nitride epi, especially in MOCVD, you can have magnesium carrying forward through these layers. And so, so it can sometimes be hard to create an abrupt p-n junction, and we think that some of that is probably feeding into why we don't exactly get the 20 nanometers thickness there that we anticipated. And so this was one important result for us to understand what was going on in these devices. And I will briefly show this so I make sure I have enough time for the next section. We also did CV on these devices, and from the slope of the CV, we're able to go and back out what the doping concentration is inside here. And so now, electrically, we can also see that we've got 1E18 doping in these regions, which is in agreement with the SIMS results that we have as well. So we have a couple ways of showing that we have consistency of doping incorporation within these structures. So yes, this CV analysis matches with SIMS as well. So this is sort of a very unique approach to making these super junction structures with these lateral polar junctions. Up until now, we had not been able to demonstrate charge balance between these, and so that's a major, major development in this area. As I mentioned earlier, when we're just growing nitrogen polar GaN, we can see the low 17s doping. We're working to try to get that alongside charge balancing in the lateral polar junctions. And I've also shown you a few different pathways to be able to engineer these Schottky contacts to tune the barrier height and reduce leakage currents, and even pathways to making high temperature devices as well. And these are some of the areas that we're currently pursuing to take this and make it a more practical implementation of these devices, from increasing drift region, decreasing doping, getting better control of these interfaces for the camel diode design, and then scaling these things down to submicron pillars. And of course, you may have noticed this, a lot of what I showed in this particular case is on sapphire substrates. These are all quasi-vertical devices. We'd love to be able to move this over to gallium nitride substrates for truly vertical devices as well. So this is a very active area for us, but I think a lot of room to grow as well. So now I'm going to switch gears to a different approach to selective area doping and a different device that we're thinking about as well. So this is work that we've been doing to leverage magnesium implantation for p-type doping in GaN and the formation of JBS diodes. So if you look through the literature, what you'll find is information like this about the challenge of doing selective area doping with ion implantation in GaN. Effectively, the problem that you have is that you will implant, and then after you implant, you will have generated a whole bunch of damage in your material, and you need to come back and anneal that material at a high enough temperature to repair the crystal and activate the implanted impurities. Now, for something like gallium nitride, the temperatures needed to repair the crystal and activate those impurities are very, very high. They're above 1,000 degrees Celsius. And at those temperatures, the material actually also starts to decompose. And so now you have this problem that you can't just throw it into a conventional RTA, for example, and just activate everything and start moving forward. So one of the things that people have done is to look at the use of different capping layers, effectively materials that you can deposit on top of the semiconductor before you do the anneal to kind of hold the material together. But the main challenge that has come as a result of that is that at these high temperatures, the capping layer and the GaN actually start to interact, and it becomes very difficult to remove that capping layer and leave behind a clean surface to which you can make high quality contacts. So we've been looking at an approach to doing this that does not involve a capping layer. And the idea behind this is to use ultra high pressure annealing. So instead of relying on a capping layer to hold the material together, let's heat this material up in the presence of a very, very large nitrogen overpressure. And we started off by doing this in 1 gigapascal, so very high pressures, but have more recently scaled this down to a few hundred megapascal. Now, if you're involved in this area and you've built tools before, you probably realize this is a gigantic number. So there are very few places in the world that will do this for you, and we're lucky enough to have a collaboration with a team at the High Pressure Institute in Poland where we send our samples, and they have a system set up for being able to do this. So effectively, at these high temperatures, we can go to up to 1,500 degrees at high pressure and prevent decomposition of the GaN, and then look at recovery of the material and activation of the implanted magnesium. And so for this first experiment, what we did is we implanted the magnesium, and after we implanted the magnesium, we went and annealed it at 1 gigapascal and nitrogen overpressure at 1,300 degrees, and relatively long time as well, about 100 minutes here as well. This is some materials analysis on these structures that we did along with Zlatko and Ramon. So importantly, I mentioned I don't want the surface to decompose. You can see here AFM morphology and roughness is similar before and after that anneal. So we're holding the material together. And XRD, if you look at this as well, you can see that when you do the implantation and do the XRD directly afterwards, you have these peaks that are indicative of damage in the crystal, but after the high pressure anneal there, you're able to remove those peaks and return back to the high quality GaN as well. Now, SIMS here is also something that's very interesting, especially from an electrical design perspective. You have this very sharp magnesium implantation distribution here, which is, this is SIMS captured on the sample right after implantation. And you can see that we designed this for a shallow implantation depth. We basically were trying to use this for contact layers. But when you do this high pressure annealing, for the temperatures and the time that we're doing it, the magnesium actually redistributes. It diffuses through the material. And so this is actually quite interesting because I mentioned earlier that wide bandgap semiconductors don't typically have We don't typically think about diffusion of these impurities, but for GaN, and especially in the case of magnesium, that's very different from silicon, that magnesium will move on you quite a bit. So you have to think a lot about that when you design your devices. And I would also argue that there may be opportunities here to leverage this for device fabrication in the future, kind of doing similar things to what people did with silicon that we maybe weren't thinking about when we moved to something like silicon carbide. A little bit of haul here. I'll just point out that once we do this activation step, we're able to see high hole concentrations as well as high mobilities. And if you work through the literature and these numbers in this chart here, you'll see that the implanted p-GaN layers have mobilities on par with what you get with epitaxy. So we're able to achieve high quality material there as well. So again, I want to see a device. What I showed you previously is a lot of the material science behind it, but I want to make a device. And one of the first devices we made was actually just trying to make a PN diode. So we did this now on a conductive GaN substrate, implanted magnesium, annealed it, and then made a truly vertical now GaN diode where we're making a backside contact. Another feature of this design here is that we created beveled edges. These are low sloped edges of the device, and if you go through the design and engineering of these types of devices, that helps to distribute your electric field and bring it in from the surface so that you can really leverage the bulk high critical electrical field of GaN. And so this was a reverse bias characteristic that we got for this device, and you can see that it's breaking down at about 1 kV. So this was one of the first devices that we were able to make. Very, very happy with this result originally, but we knew that there were a lot of problems. And what I'm not showing you here, for example, is what happened when we make Schottky contacts on these samples that went out for annealing. So we had good breakdown voltage, but the surfaces for the formation of contacts were clearly not ideal for us. And so one of the things that we've been doing over the last couple of years is thinking about different surface treatments that we can use to improve the performance of these devices. And so before I get to that, I just want to show that my student did some modeling here to try to understand what the distribution of the electric field is. He also tried to match the simulated distribution of magnesium to what we had through SIM, so it was kind of a better representation. And you're able to see that we're getting critical electric fields that are near the ideal in that 3 to 3.3 range for GaN. So we're leveraging the GaN at its maximum here. So this is very recent work. It's actually just been published. And over COVID, we were really banging our heads up against the wall trying to figure out how to make good contacts to this material, right? So not just showing that we can deal with high electric fields and large reverse bias, but also forward bias characteristics being very good as well. And so what we did is we went ahead and wanted to demonstrate this through our target device, which is that JBS diode, where now you are creating a grid of implanted P regions. We mask the sample off with resist, basically send it off for implantation, strip the resist, and then send it off for ultra-high pressure annealing in Poland. You can see here that we've been tweaking our conditions a little bit with a lower pressure here, slightly lower times as well for anneal, and then we create these devices that have this kind of structure with these P stripes as well. So the best way that I can really convey to you how good the surfaces are now with the improved processes that we have is through this Schottky contact, because as we know, Schottky contacts are very, very surface sensitive. And so this is a control Schottky diode that we make on that same wafer that's gone through all these processes. In this case, it's Schottky contacts, so there's no implanted region here, but it has gone through the anneal. And we can see near ideal Schottky barrier contact, Schottky behavior here as well. And actually, one of the things that's particularly fun for us is we kind of worked through and did some calculations for what we could estimate the mobility in these regions in the drift region to be, and we're seeing what we think are very, very high vertical mobilities of near 1,000 centimeters squared per volt second. So this shows that we're getting low doping, 1.3 times 10 to the 16. I have separate CV for that to demonstrate that as well, but I'm not showing here. But we're also seeing low losses, which are coming from the high mobility in these films as well. So low carbon incorporation basically as well. This is, yes, the CV that we have here to demonstrate the 1.3 times 10 to the 16 doping inside here with the low built-in voltage as well. So now you may be interested, okay, well, what's the JBS diode doing? So now we have the JBS diode that I'm putting side by side with this. And now you can see through this chart here that we have the JBS diode with slightly higher turn-on voltage. And what I didn't really tell you earlier about why I'm doing this JBS diode is that I'm willing to pay this price of a larger resistance, I should say, but because what I'm getting in return is a lower leakage current and reverse bias. These are all measured results over here, where I have a Schottky barrier diode, sort of the control one. I have one with an edge termination. I have my JBS diode here, and I have another PN diode that I created on the same sample. And what you can see here is that Schottky barrier diodes, because they're very surface sensitive, have more leakage current, barrier lowering effects are happening there. But with the JBS, I am in reverse bias merging these PN regions, basically driving the junction below the surface and reducing my leakage current here. And now I'm able to show that I can get breakdown voltages on par with a PN diode on the same wafer. And so where do all these things stack up? If you look at what's been published in the past, we have now demonstrated for GaN devices record RON at 900 volts here. This little unfilled arrow is sort of what we think is also maybe a path forward here. If you go ahead and you thin the substrate as well, you should be able to reduce those losses even further. But even with the thicker substrate that we have here, you put the whole thing together, we still have record RON and performance here for these devices. So I'll wrap up here to make sure that there's a few minutes for questions. But basically what I'm demonstrating here is our ability to use magnesium implantation in conjunction with ultra-high pressure annealing to achieve p-type doping in GaN. We use that UHPA approach to recover damage and activate the magnesium. And through Hall measurements, we can show that we have high p-type conductivity on par with epi material. And these low ideality factors that we're showing now are very, very promising. We have really tuned in this process a lot, and we're able to get good contacts and good behavior from these devices with low resistances that come from that as well, which are really record-breaking compared to what was published up until now. And so overall, between the LPJ and the magnesium implantation approaches, we're closer than ever to selective area doping in gallium nitride. You know, if we make these super junction devices scaled up to higher voltages, I think that could be a real game changer in the power field, especially because we can do this at scaled approaches that could really go beyond what silicon carbide is able to do with more conventional cases. And now we're even unlocking JBS diodes at high voltages, which I think will be very, very promising for next generation electronics. And the last teaser that I have here, which is sort of something I skipped over, is this question of can magnesium implantation be used for superjunction devices? In the sense, can I make these pillars side by side and then drive the magnesium down via the high pressure annealing, and now look at an alternative way of making superjunctions as well, in a way that would not be something that you can do in silicon carbide. So this is kind of an interesting question that we're thinking a little bit about as we move forward. And yeah, these are some of the folks that have funded this research. And if you have any questions, I'd be more than happy to discuss them offline as well. Thank you very much for your attention. I'd be happy to answer questions. Thanks.
Any questions from people who are electrical engineers, not me?
Very nice and clear talk. I'm curious about the high pressure annealing.
Yes.
So what is the mechanism that, so what changes? The activation energy for both dope and incorporation as well as the activation energy for diffusion? Are both of those changing when you go to higher pressures?
So that's an interesting question. I don't think we are changing those parameters as much as we are allowing the GaN to be contained or not decomposed at those temperatures that are needed for the activation to occur. So in other words, if you could, for example, use something like a capping layer to be able to sufficiently control or contain the GaN at a high enough temperature, I think you might see similar activation energies in something like the high pressure annealing technique that we use or in a capped approach. The problem is that other techniques that people have looked at using for annealing these things, the GaN typically degrades at those temperatures that you're needed.
So you're still annealing at the same temperatures as you were before. You did not lower
That's correct. We've lowered it a tiny bit from what we did early on at like 1400 degrees. Now we're still at 1300 degrees or something like that. So it's a small reduction. But yeah, we're not using the pressure to come down in temperature. In fact, it's sort of the opposite. We're using the pressure to be able to stay at the high temperatures that we need to activate. Yeah.
Hey, Spyros.
Yeah.
Thank you again for the talk.
Sure.
On the maybe the next to last slide, the JBS diode, where you have the selectively patterned p-doped.
Oh, sure.
So you showed the magnesium drive-in. Did you design those to account for the spread, the lateral spread?
Yeah, that's a good question. We have. We still need better control over that as well, but definitely through a lot of experimentation, we have an idea now for a given doping profile, initial implanted doping profile, and then a set of conditions that we use for annealing where that magnesium should finally end up. And then as a result, we can design our device to be able to handle that. So what we've seen, and there's groups out of Japan that have been working very actively in this area as well, is that we mainly see diffusion vertically, and then the lateral areas outside of where we did the implantation actually do not allow the magnesium to penetrate into those that efficiently. So it seems to be driven by a damage initially, and that allows quick kind of movement of the magnesium. And then once you fix that or repair that crystal, the magnesium diffusion kind of slows down as well. So it's mainly accounting for vertical movement or diffusion of the magnesium there. But yeah, that's definitely been something we've been thinking about.
Any other questions? All right, if not, okay, got it under the wire.
Yeah, a very nice talk. Also curious, so for the vertical is P and N. So especially during high temperature annealing, what happened between the interface? There is non-diffusion. I still very not that clear.
You're asking about like this lateral interface here between P and N?
Another device, a picture. So you have very big.
Which picture?
Okay, maybe back more. Yeah, even more. So you shows the interface.
Are you talking about like these pictures?
Select vertical. One is the P.
Oh, the lateral polar junctions, the earlier part of the talk? Like this stuff here, right here?
Yeah. So you see one big is half is P, another half is N.
Yes.
What happened between the P and N? So there is very long interface.
Yeah, so let me go back a couple more slides. Here. Oops, here you go.
Yeah, you can.
So we are doing two things, right? So we are, through the initial patterning of that aluminum nitride template, we are controlling how the growth will initiate and what polarity the GaN will have as it grows vertically from there. So we can control it so that it's gallium polar or nitrogen polar based on whether or not that aluminum nitride template is there. And then those grow side by side. And then after that, you can control based on what you're injecting into the reactor, for example, whether or not you're putting magnesium, whether both will be N-type or one or the other will be P or N, or actually if you put enough magnesium in there, they could even both be P-type. And so we are, this paper actually, if you look at the title here, this was a paper that was led by Zlatko and Ramon, sort of, you can think of it almost like three-dimensional doping control. You can control the doping laterally between those nitrogen polar and gallium polar regions based on what is being incorporated into those films. But by tuning what you're putting into the reactor as you go vertically, you can also control the vertical arrangement of those layers, the doping in each of those layers vertically. So we are, as this cartoon previously sort of shows here, we are growing these gallium polar and nitrogen polar regions side by side, and then we're able to control whether each one of them is P or N. I'm not sure if I'm answering the question, though. I want to make sure that I'm addressing it.
Yeah. So, but during high temperature annealing, what happened between the P and N?
Okay,
There is some lateral diffusion?
Okay, sorry, yeah. So this sample, we do not do this ultra-high pressure annealing. So these are two completely separate approaches. The ultra-high pressure annealing that I showed at the end of the presentation is something that we're leveraging in combination with magnesium implantation. So that is to repair the crystal and activate the implanted magnesium. In this case, the magnesium is incorporated during the epitaxy itself. And so we follow up with a lower temperature anneal to drive out hydrogen, which is very typical for MOCVD growth when you're trying to do P-type GaN. But we don't do an ultra-high pressure anneal. And so we don't expect there to be lateral diffusion or even, for that matter, significant diffusion as a result of annealing steps. You may have a sort of smeared profile of magnesium because of other things related to the growth step itself and magnesium being in the chamber and so on, but there's no anneal that we're doing to move the magnesium around after the structure is grown. Does that answer your question?
Yes, but this is the theoretical condition, the scenario, right? So there should be something between the PN and in the interface in reality. So.
What do you mean by something in between? I guess maybe.
Oh, yeah, you go back to last draft. So
Okay.
there should be some, this is the PN junction lateral, right?
Yes, yes.
So
yes.
does that affect your device?
So is there a current flow or something like that?
Yeah.
So, okay, so keep in mind that current will flow kind of following the lowest barrier, right? So these PN junctions have large barriers between them, right? With GaN, right, you'll have a 3.4 AV barrier there that you have to surmount. So these barriers here, this is designed, this is the camel diode, so this is a little bit of an exception because it's thin and we're depleting it. But after it climbs through that, it's going to go through the lower barrier pathway, which is down here. So we don't use the gallium polar or this P-type region for conduction. We use this to balance charge, which gives you that difference in E-field distribution, which then leads you to have the lower conduction losses basically in the superjunction structure. So this, if I, in other words, bias this device at, let's say 4 volts or 5 volts, then I would turn on this pathway as well, and I could inject current all the way through this as well, and then I'd have a PN junction or bipolar conduction as well. But in this case, I would restrict myself to 2 volts, let's say, in which case I'm only providing enough bias there to go through this side, and this is just there to passively balance out the charge when I'm in reverse bias.
Okay, great. Thank you.
Sure.
Thank you.
I'm also happy to talk afterwards if I'm not addressing the question 100%.
No, good discussion, but I think in lieu of the time, we will finish up. And so let's thank Spyros one more time.
Thank you very much.